All right, so welcome back. So today we will be talking about an interesting topic, which is reinforcement learning. So remember that we have four main topics. So value-based decision-making, risky decision-making together with intertemporal choices. And then the third one is motivation and emotion in decision-making. And the last one is social decision-making. And after the four main topics, we had a small applied session on consumer neuroscience to see how the studies can be used in real life, for example, when we were designing packages, when we were trying to increase profits as a businessman, for example. And we had last week the open science guest lecture. So the idea is that we try to make everything open and replicable and reproducible, and basically to improve our best practice when doing science. So before we move on to the final group presentation, we will have our last two lectures. They will be a little bit more advanced in the sense that they move a little bit more beyond the basic or simple decision-making. So the first one is this week. So we will be focusing on something called the reinforcement learning. And then the week later, the next week, we will be focusing on game theory inspired decision-making games, okay? So let's get started, the reinforcement learning. The warm-up part is what I said already, and now we talk about reinforcement learning. So before we dig into the idea of reinforcement learning, so I would like to repeat the idea that I mentioned multiple times already in this seminar, which is cognitive modeling or computational modeling. So computational modeling, maybe to some of you, it is quite new, but I would like to try to convince you that the idea of computational modeling is never new. In fact, it has been more than a few hundred years, even though it is not really used by cognitive scientists or psychologists, but the models or the computational methods, they have been used by physicists for a really long time. There's a long history about that. So for the computational models, the simple concept is that the scientists, they would like to use mathematical models to approximate certain processes. So this process in the history, it can be physical, and nowadays it can be mental process, cognitive process. And the goal is always to explain and then to predict. So as a very simple example here, this is from very few hundred years ago, right? The physicists, they would like to predict the trajectory of planets. And then there are two models, one is the circular one, the other one is the elliptical one. And both of them, they are models already, and then they make different predictions, and then they make different hypotheses. So in this case, it is a physical process, and what it's going to be when it is cognitive process. So this figure I showed you earlier in this lecture, week 2 or week 3, when we were trying to describe or discuss different methods in decision neuroscience, and one of them is cognitive modeling. So here the simple idea is this is the participants, and we record behavior or brain responses from the participants. So inferring from the behavior back to what might be happening in the brain is quite challenging. It's like a black box. We do not know, right? So instead, researchers, they propose mathematical models that are trying to approximate the cognitive process in the brain. So here, this one, it is a cognitive model with the goal to approximate the cognitive process, as I said. And the model, it is a few lines in a text file, honestly. It is a script. If you know programming, basically that is a script. And then we can use the script to make predictions. And we could compare the model predicted behavior versus the real behavior we observed from the participants. So here it is the model predicted behavior, and here is the real behavior. And if the predicted behavior matches the real behavior, we could say, well, this cognitive model is a good approximation to what might be happening in the brain when the participants are doing the task, okay? So this is the idea of the cognitive modeling. And as you could see, cognitive models, there are many types of cognitive models, and one of them, it is quite influential and dominant. Then that is today's core topic, the reinforcement learning model. So the term reinforcement learning model doesn't really come from psychology or cognitive science. It instead came from the field of computer science or machine learning or artificial intelligence. A very short story is basically I show you the book cover of the book of course, reinforcement learning. And this book was written by two computer scientists, and 1998, it was the first edition, and 2 years ago, they updated a lot of that content in their second edition. Interestingly, as I said, because the book, it was focused a lot on computer science, so nearly all the content in their first edition, they focus on computer science related stuff. And over the past 15, 20, or even more years, so even the computer scientists, they actually realized that how the concept or how the framework of reinforcement learning actually helps the development of psychology or neuroscience. So if you're interested in the second edition, they actually included quite a few chapters about psychology or cognitive neuroscience. Okay, good. This is very simple or short story. And so how does the framework look like? This is the question, right? So the reinforcement learning basically describes the relationship between the agent and the environment. The agent can be a person, can be just like you, right? So this is you as a person, and you are interacting with the environment. The environment can be just the outside world, or can be the environmental setup, the experimental setup in the laboratory. And then the environment is unknown. And only when you are acting towards the environment, you will be getting the feedback from the environment, and then you can learn from the experiment. So only through interaction, you can learn how the outside world looks like. So this is the conceptual idea. So judging from here, you see this is a person. The person could make some actions. Action, this can be a decision. So we are talking about decisions. So there are choice alternatives, and then the individual could make a choice. So then this choice will result in some feedback. So either a positive feedback or a negative feedback, for example. And then the feedback is given from the environment. And then the feedback is observed by this individual. And then this goes back and forth for a few times, so to facilitate the interaction between the person and the environment, okay? And if you follow the news from a few years ago, there is the game, okay, between artificial intelligence and a Go player. So the artificial intelligence in this case, it is called AlphaGo. So in essence, the AlphaGo also utilizes a reinforcement learning algorithm that is just a little bit more complex than what we will be covering today. Okay, like this, there are multiple layers. To make it a little bit simpler, so we will use one example to introduce you the reinforcement learning framework, so how that can be used to study behavior, right? We are not really focusing too much on computer science. We are focusing on to understand cognition and the behavior when people making decisions. So usually when people are running this kind of tasks, so researchers, they use slot machines or bandit machines. So in this case, both of them, they are bandit machines. So let's assume that one bandit machine is a little bit better than the other. Better means if you play that more often, if you play that, it will return you more often positive reward relative than the other. So this is the definition of better. So you receive positive feedback more than the other one. And here, so why it is called a two-armed bandit task? It is because this is one arm, this is the second arm. together, it is a two-armed bandit task. So each time you have a decision to choose from. So decision making, right? This is what we have been talking about. And suppose that you are presented with the two slot machines. You are a person, or maybe you enter a casino and you are standing in front of the two slot machines. And you would like to know, well, which one do I play? I have no idea at the beginning which one is the better one, which one is the worst one. So the only way to find out is to play with it, is to pull the lever and then to see what the outcome will be, okay? And then you play it, you receive feedback, and then you play a second time, you receive a second feedback. You use the feedback to update your learning. So you learn from feedback. So the simple task here is the bandit machine task, and you repeatedly make the choice between the two choice options. And the two choice options, they have a reward probability. So reward probability means how likely that you will receive a reward. And then the goal is to maximize the reward. So if you go to the casino, there are two machines in front of you. I tell you that you can only play 50 times, 50 times. And then what can your strategy be? So think about it, right? If I tell you, you can only play 50 times, and then how you want to behave? Maybe you make the choice randomly at the beginning because you have no idea which one's better, which one's worse. But after playing a few times, you figure out that maybe one is better than the other. And do you stick with the one that you think is better, or do you sometimes switch also to the other to explore the other opportunity? So those are strategies. Okay, good. So what can be the strategies? Usually it can be that you could break down into multiple steps. The first one is to predict the value of each deck or the value of each machine. So you make a prediction which one is better, which one is worse. And then you behave accordingly. So you make the decision according to your prediction. And what you will receive is the feedback. And what you do next is to learn from the feedback. And then the learning is used to update your prediction. So when you receive the feedback, you update your prediction. And then on the next trial, you behave accordingly according to your updated prediction. Okay? And you repeat this one, of course, multiple times, according to how many times you are allowed to play. So the how many times here means the trial, the experiment. So linking or connecting this framework to what we have known already, then I will show you this graph. So this graph we have seen many, many times throughout the entire seminar. So here, I just briefly show you again. The representation in this case means there are two machines in front of you. You have to play with the machines to gain money, right? And then the valuation is the prediction here. You will make predictions regarding which one is valuable, which one is not valuable. And then you behave, you make the decisions accordingly, according to your prediction, according to your value. And you will receive feedback from your action. And then you use this feedback to learn to update your prediction. So this is the idea, and now everything is connected. So here, here, or here, they basically mean the same thing, at least in our today's lecture. It can be more complicated in the real life, but at least in the lecture here, these three pieces, the text, this graph, and this chart, they mean the same thing. Good. And in real experimental setup, usually we do not present participants with two slot machines because the symbol of a slot machine, it is too rich in terms of the visual aspect. There are too many colors and here and there, and the people might get distracted by looking at the slot machine symbol. And instead, what we usually show to the participants are abstract symbols. For example, imagining this is a screen in front of the participants. They are sitting in front of a computer, and they see, instead of two slot machines, they will see abstract symbols. No meaning, just abstract symbols. And what they are asked to do is the same as if they were playing with the bandit machine. So they were presented with 2 choice options. They make a decision, they receive feedback, and then they learn which one's better, which one's worse, with the goal to maximize the overall outcome. Okay? So here, 2 options, and make a decision, choosing blue, getting a reward. Next time can be that they choose, well, they repeat the blue option, but maybe the second time the person is receiving a negative feedback. Okay, good. So this is the task. And the researchers, they were trying to use the reinforcement learning framework to analyze the data, to use cognitive models to quantify the possible cognitive processes when the participants were making the task, when the participants were making the choices. So here, there are 3 stages, if you wish: the choice presentation, the action selection, and the outcome learning. So you can basically ask yourself what you know already and what you can measure and what you do not know. So if you are an experimenter, if you are running the study, and if you collect the data from real participants, what are the data? So the data is not so, so this question is not so challenging to answer, I guess, because there are not too much to be recorded from the participants. So we record the choice from the participants, and we record the feedback from the participants. So what we know is choice data and outcome data from the participants. So what we can measure is that we can calculate how often the participant is choosing the better option, and then this is the accuracy, and we can calculate the accuracy per person, okay? And then this is already the finish, the end point if we do not use cognitive models. So we give a task to the participants, we analyze their accuracy, and then that's it. That's already the end of the story without a model. But if we want to use a model, what is the question that we can ask as an experimenter, as a researcher? So the question we ask, in other words, what we want to know is that we would like to know what is the possible learning algorithm under the reinforcement learning framework. So out of all those families of reinforcement learning models, there is the simplest one. So the simplest one is actually from psychologists. In this case, it is the Rescorla-Wagner model. In the very beginning, originally, it is developed to explain Pavlovian conditioning data from animals, but actually it is also very powerful to explain human behavior. In this case, I will show you in a minute. So the central idea of the Rescorla-Wagner model is that it is an error-driven learning. So what is the error here? How does that drive learning? It is described by 2 lines of mathematical formulas. So don't get scared, don't get scary. So these are some simple terms, honestly. So I will also slowly guide you through that. The error-driven learning part, it is quantified by 2 lines of mathematical equations. So the first calculation is that people have to calculate the reward prediction error. So the reward prediction error basically means what you actually get minus what you expected that you would get, okay? So here what you actually get can be nothing but a positive or a negative feedback. And if you want to do it in software programs, the win can be a +1, +1, and then the loss can be a -1, a -1, a loss, okay? So this one basically this one can only be +1 or -1, 1 - 1. And then this is the expectation. And the difference between the actual feedback and the expected feedback, that is the reward prediction error. The reward prediction error is then multiplied with a learning rate. So this is called a learning rate to update the value. So here there's the new value, here there's the old value, and then the value is updated by a learning rate weighted reward prediction error. Okay, so if that doesn't make too much sense, I will try to translate that into some human understandable language. So that means these two lines, they mean that expectations on the next trial. Expectation means how do you think each stimulus will give you a reward. That's the valuation, right? Expectations on the next trial equals the expectation on the current trial plus a learning rate multiplied with a prediction error, and then the prediction error is the difference between the actual reward and the expected reward. And then the expected reward is basically the expectation on the current trial, okay? So this is the idea, the entire idea of the Rescorla-Wagner model is these two lines. Good. I guess people like examples, and then we can see one example here. So assuming that the value of the learning rate is 0.9, and also assuming that the initial valuation is 0, and then after receiving one positive feedback, what the value is going to be on the next trial. So here we basically to say, well, initial value is 0, and then the new one equals the old one plus the learning rate multiplied with the prediction error. The prediction error is the actual reward 1 in this case minus the previous feedback, the previous expectation. The previous expectation equals 0, not surprisingly. And then we do this calculation, we see that the next value becomes 0.9, okay? And if you see here in gray color or in black color, gray color, so this is the actual feedback to the participants. So the participants receive a win, 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 multiple times of win, 5 times of win in the beginning. And then the participant receives twice of punishment or loss, and then followed by a few more times of reward and 1 time of punishment. So this is the actual feedback we deliver to the participants. And then the purple line here, that means the expectation from the participants. So basically the participant is learning from feedback, and then the expectation more or less follows the true structure of the task. So you see how the model works, and it is actually really powerful to resemble the task structure when the participants are learning and when the participants are making decisions. Okay, good. So when we have the value, or when we have the expectation of 2 options, so we have the value of the yellow option and we have the value of the blue option. And the next step is to make a decision. So I said that the decisions are made according to the values. So how this accordance is implemented in reality. So there is a soft max choice rule. So in the sense that participants are making choice according to the difference between the values, okay? So here what is plotted is that on the x-axis, the value of the yellow, for example, minus the value of the blue. And then the y-axis is the probability to choose the yellow option. So what you can see here, the larger the value difference, doesn't matter this number here. So maybe let's look at this line, the solids and the darker line, this one, purple. So the larger the value difference, and the more likely the yellow option will be chosen. So it doesn't really so surprise. It is not really so surprising, right? Because if you imagine that you have a value of yellow option, you have a value of blue option. If the difference is larger, you believe that the value of yellow is better or larger than the value of blue. So then you will be more likely to choose the yellow option. On the other hand, if the value of the yellow is small, and maybe if the value of the blue is close to the value of yellow, so you will have a hard time in deciding which one you will choose from, which one you will be choosing, okay? So this is not so challenging to understand, I guess. So what this line does is basically to convert action value to action probability, okay? So the detail you do not really have to vary too much. but the curve, the shape of the curve is more important. All right, good. And because we are talking about decision neuroscience, we talked about decision according to the model. We also have to talk a little bit more about neuroscience. So how does the neural part come to us? So when they were trying to analyze the functional neuroimaging data, the both signals, the researchers could utilize the expectation, so the value, and the prediction error they derive from the model to analyze the brain imaging data. So here, the same task, making a choice and then get feedback, and then at the same time, the brain responses are recorded by the MRI machine, the both signals, and the V is the expectation, and then the delta, it is the reward prediction error. So those signals can be entered into data analysis. And usually in the literature, what you will see is that the expectation, they are very often associated with brain responses at the VMPFC, the ventral median prefrontal cortex that we have heard about many times. And then the prediction error, it is associated with another brain area, which is the nucleus accumbens or ventral stratum. This is also another brain area that we have been hearing pretty often throughout the entire seminar in the semester. Okay, good. And what I would like to say is that today the topic is maybe a little bit too advanced. So there are some mathematical details. You do not really have to worry about that. So you will, what I would like you to remember out of today is that there is something called reinforcement learning. It is very useful. It can be used to analyze data. It can be used to design experiments. And then that's it. The detail, you really don't have to worry about that, okay? At some later point, if you decide to do a master or even PhD, and if you think that is useful for your own research, you can come back. So here today, I provide you with the starting points. And then later, if you think that it's helpful, you go back. You do not have to remember too much about the contents today, okay? Okay, good. So before we move on to the presentation, let me just talk about one last thing. So I said that the reinforcement learning framework is useful or powerful. It can be used to design experiments. So it basically can be generalized to other contexts, not only monetary reward, it can also be social feedback. So example can be, so here, this is a good example. Participants, they are presented with two abstract symbols. The participants make a choice, the participants receive a feedback. Same idea, right, as what we have seen. So the experimental setup is interesting in the sense that there are three conditions. So one is that you learn, and then the points will go to yourself. So this is self-learning. And then this one, suppose you have a good friend and whose name is Louis. You learn, and then the money will go into Louis' pocket instead of yours. So basically you learn, you earn money for your friends. And then this in their term, it is called pro-social learning. And then in the last condition, nobody will be gaining the money from your learning. So this is a nobody condition, as a control condition. And people could compare if self-learning is the same or different from pro-social learning, okay? And in other scenario, the researchers could also use social feedback as a feedback type. So we talked about monetary reward, either a win or a loss. So here the participants, they are seeing a like or a dislike. They are social feedback from the others. So here, some people, they are nice, so they give most of the time a like to the participants. And here, those people are a little bit mean, so they give less often positive feedback to the participants. But the entire idea is the same. You make a choice and then you receive feedback, and then you use the feedback to learn, to update your prediction. So this is the simple or the core idea from today. Using feedback to learn, to update your prediction. So this is the take-home message from today, okay? Good, any questions? Sorry I was a little bit fast, but I guess this is convincing. I hope I have convinced you that the framework, the reinforcement learning framework, is useful and interesting. It can be used for anything, even as complex as building artificial intelligence. And if you do not follow, that's the advantage of recording. So you are feel free to watch later on. And any questions before we move on to the presentations?